Hi everyone, this is Mrs. GA, and today we're going to talk about tangents and circumscribed angles. So a tangent is a line that's in the same plane as a circle and that intersects the circle in exactly one point. So you can see over here we have this line that is intersecting this circle at exactly one point, point P. So if it's only intersecting once, it's always going to be on the outside of the circle, and again, it just intersects at exactly one point. The point where the tangent and the circle intersect is called the point of tangency, so that would be point P. So first we're going to learn about the tangent radius theorem. So this theorem states that if a line is tangent to a circle, so here you can see we have a tangent line, then it is perpendicular to a radius. So here's a radius that is drawn to the point of tangency. So you can see here, we know it's a radius because it goes from the center to the circle. And again, you can see that it is touching your tangent at the point of tangency. So that angle will always be 90 degrees. Now remember, the converse is just switching the if and then. So the converse of this theorem says that if a line is perpendicular to a radius at a point on a circle, then it is a tangent to the circle at the point. So that proves that it is a tangent line. Okay, so let's look at this first example together to see if we can use the theorems we just learned to help us find different parts of this figure. So here, we know that AB is tangent to circle C at point B. So here's AB, here's our point of tangency. We're also told that AD is tangent to circle C at point, this was supposed to say D. Go ahead and fix that on your notes. And here we're asked to first find the measure of angle ABC. So notice AB is a tangent and BC is a radius. So according to the tangent radius theorem, this angle should be exactly 90 degrees. They are perpendicular. Okay, next we are asked to find the measure of angle DCB. So to do this, it helps to look at a larger quadrilateral in this figure. So look at what I just highlighted in blue. So in this quadrilateral, we know that this angle is 90 degrees. And we also know that this angle is 90 degrees because, again, I have a tangent and a radius, so they are perpendicular. And then I know that this angle is 40 degrees, and I know that in a quadrilateral, the angle should add up to 360. So we say 360 equals 90 plus 40 plus angle DCB right here, which we're trying to find. So angle DCB should be 140 degrees. And this problem will actually turn into a theorem that we're going to learn about on your next page. Okay, next we are asked to find the measure of angle BDA. So for BDA, it may be useful to look at this as a triangle like this. So if you think about it, if we have a single point on the outside of our circle that both tangent lines go through, we can infer that the distance from A to B should be exactly the same as the distance from A to D. Again, since both are tangent lines, meaning they're both hitting at exactly one point, these two tangent lines should be congruent. So, since we know that, we can then use the Triangle Sum Theorem, and we can use the fact that this is an isosceles triangle. So in an isosceles triangle, the base angles should be congruent. So this base angle BDA is what we're trying to find. So if this angle we can call x, the other angle we could also call x. So using the Triangle Sum Theorem, we could say 180 equals x plus 40. So we get x equals 70 degrees. And then last, we're asked to find the measure of angle CDB. So again, we already know that this angle right here is 140 degrees. So if I look at this triangle, triangle BCD, again, we know this angle. CB is a radius, so it should be equal to CD because all radii should be the same exact length. And here, again, we have another isosceles triangle, which means our base angles should be congruent. So CDB is one of our base angles. So we'll call it Y in this case. And then we can do the triangle sum theorem again. So 1 at 180 equals 140, which is the angle DCB that we found earlier, plus Y plus Y. So we get Y equals 20. So that angle is 20 degrees. Okay, so now we're going to kind of put into words some of the things we found out in the last example. But first we need to learn a new piece of vocabulary. So this is called a circumscribed angle. So a circumscribed angle is an angle formed by two rays from a common endpoint that are tangent to a circle. So what does that mean? Well, first let's start with this common endpoint. So if you look at this figure here, we do have a common endpoint right here at X, and then here we have ray XA and ray XB, which are both tangent to the circle. So this angle formed, angle AXB, is what we would call a circumscribed angle. So the circumscribed angle theorem says that a circumscribed angle of a circle and the associated central angle, so again, this would be the associated central angle. Remember, a central angle has a vertex at the center, and it's associated because they have the same endpoints here at A and B as our circumscribed angle. So those two angles here and here are always going to be supplementary. And remember, we found that out in the last example because we know this angle is 90, this angle is 90, and they should add up to 360. So again, we could say angle X plus angle C should equal 180 degrees. They are supplementary. A corollary about tangent lines intersecting at a common endpoint outside the circle. We also talked about this as well. If two tangent lines intersect at the same point outside the circle, we know that the distance from that endpoint to your point of tangency should be the same. So Km is congruent to Kn. Okay, so now let's look at example 2 together. So it says QM is tangent to circle P at point M, and QN is tangent to circle P at point, sorry, we have another mistake here. This should say point N right here. And we're going to find the following. So first we're asked to find X. So notice here that we have a central angle and a circumscribed angle. And they are associated with each other because they share the points N and M. So these two angles should be supplementary. So we know that angle P plus angle Q should equal 180 degrees. So that means 2x minus 7 plus x plus 1 should equal 180 degrees. So we're going to combine like terms. 3x minus 6 equals 180. 3x equals 186. So x equals 62. So now that we know what x is, we can find angle NQM using substitution. So it's going to be 62 plus 1. So angle NQM equals 63 degrees. Next, we're asked to find measure of angle PNQ. So again, we're going to use that tangent radius theorem, and we should notice that these two segments are perpendicular, so it should be 90 degrees. And then angle NPM. Here again, we already know what x is, so we can find that by substituting. So angle NPM is 2 times 63 minus 7. So angle NPM is 119 degrees. Okay, let's try this last example together, and I apologize, there's another mistake in the given, so we'll fix that together. So this says EF is tangent to circle H at point F, and then this was supposed to say EG is tangent to circle H at point G. Determine the length of EF. So here, again, if two tangent lines intersect at the same point outside the circle, remember the two segments should be congruent. So we would say 5x equals x squared over 2. And then here we have a quadratic equation. I know that because it says x squared that we need to solve for. So we can start by multiplying both sides by 2. And then here, since I have an x term and an x squared term, we're going to want to set our equation equal to 0. And then from here, you could do the quadratic formula. However, I think the easiest thing to do would be to factor. So there is a greatest common factor of x. So we factor out x. And then from here, we can do the zero product property. So that's where we take each factor and set it equal to 0 separately. So x is a factor, so we set it equal to 0. X minus 10 is our second factor, so we set that equal to 0. Here's one solution for x. Here's our second solution for x. However, we have to make sure that our solutions make sense because x is a part of a segment length. So you'll notice here, if we substitute x equals 0, then that's saying the length of this segment is 0, and that's impossible. So this is what we would call an extraneous solution because it doesn't work for this real life situation. So our only answer for x should be 10. But again, they don't want to know what the x value is. They actually want the length of EF. So now that we know what our only viable x value is, we can substitute it right here to find the length. So it's going to be 10 squared divided by 2. Remember, we should always square before we divide according to order of operations. So it's 100 divided by 2. So EF is 50 feet. Of course, we could have also substituted it right here, and then knowing that the two tangents are congruent, you would get the same answer. Okay, that is all for today's video. Thank you so much for watching.